Greetings, this is an Autodesk NetFABB tutorial explaining how to run a part level analysis. Now the objectives for this lesson are to import a CAD file into NetFABB simulation, select a suitable process parameter file for the geometry, run a part level analysis, and then import the results for viewing. In the simulation utility, we start by clicking the simulation menu in the upper left corner and selecting New. In the resulting dialog, we click Powder Bed Fusion to specify the type of analysis we're doing, and then click Create Simulation. We're prompted to import a file, so we navigate to its directory location, select the file, and click Open. In the Import dialog, we indicate that the file is a part, not a support structure. And in the Converted Model Units dialog, we check that the default settings are fine and click OK here too. The part opens on a build plate. Here we can hold down the right mouse button to rotate the part, or hold down the scroll wheel or middle mouse button to move the part. And also click the View cube for a more precise alignment. On the Home tab of the top ribbon, we can set up and run the simulation. So we'll start by clicking Machine. We'll leave the default generic Open Machine selected, but note that it's also possible to select from a range of popular build machines. In the Processing Parameters field, we select you can use the PRM file that you created in the PRM tutorial, or choose another one for Inconel 718. Click OK to close that. And we go to the Build Plate icon. And on the Properties tab, we deselect the Match Part Deposition material. And instead, we select a material from the drop-down list. We're going to use SAE 304, which is a stainless steel. You see advanced options here that are covered in other tutorials, but for now we'll accept the default settings. Then on the Size tab, what we can do is manually adjust the size of the build plate using the handles aligned with the X, Y, and Z axes. Or you may find it easier to enter numeric values in the length fields. Click OK when you're finished here. So next we'll go to the operating conditions option, and we're just going to note the settings here. We will leave these default values as is. We're not going to simulate heat treatment or adjust the mesh settings, but we will click the mesh preview to generate a mesh with default settings. Now we're immediately asked to save the model in a project, and in the top of this dialog, the proposed save location is the same place where we got the part from, so we're going to save it in a different directory of saved objects. Once that's set, the mesh generates, and in a few seconds we'll be able to see the results. So the system has consulted the PRM file and generated a proposed voxel mesh on that basis. Note that the element size in the mesh varies with the need for detail. Small voxels, where the part has fine details such as curves and edges, but larger voxels in flat areas, and especially in the build plate, away from contact with the part. Seeing this mesh gives us an opportunity to look for any mesh errors that could affect the simulation, and no errors are visible here. So we open the solver settings. On the Analysis tab, accept the default settings to run both a thermal and mechanical analysis. Hit OK to finish setting up the solver. In the ribbon, click Solve to run the simulation, which first runs a thermal analysis, recording the temperature at every mesh node for each timestamp. Then the thermal analysis results are used as input for the mechanical analysis that will determine the resulting displacement, stress, and strain. While the analysis runs, we can use the Job Manager to monitor progress. In the upper left of this dialog, we can click View Logs to review thermal and mechanical results for each timestamp. During the analysis, the logs are scrolling, so it's not easy to consult them until after the simulation run. When the analysis finishes, the results are loaded. In the browser on the left, check that the light bulb is on for displacement results. And then in the ribbon Display panel, click Warp by Displacement and set the displacement scale to 5 to exaggerate any distortion, making it more visible. Now we can click the play button in the upper left to see the displacement results. To stop the visualization at any time, just click play again. So that is the completion of our basic simulation workflow. Just to summarize the process, we imported a geometry into NetFab simulation. We selected a PRM file to perform a part level analysis, and then we viewed the displacement results.